Good morning, Professor Wang and Dr. Cheng. My name is Zhihan, and I'll be taking on the project titled Biomass Gasification in Clean Energy. Now, before we touch on the topic proper, I believe a little introduction of myself is necessary. I'm currently a double degree student pursuing a Bachelor's of Business Administration from the Business faculty on top of my chemical engineering degree. I'm pleased and extremely glad to be supervised by two renowned faculty staff. I understand that I will have to work extremely hard on this project, and I hope my dreams will come to fruition. Now, in the meantime, this introductory presentation will serve as a touch and go on my understanding of the project so far, and perhaps also provide an insight into what I have planned to achieve. I've segmented my presentation into four separate parts: the introduction, a literature review, my tentative plan, as well as an overall look at my proposed schedule for the upcoming few months. Now, without further ado, I shall now proceed to the introduction, which will hopefully give everyone listening in an eye-opener into the concept of biomass gasification. So in this introduction, I hope to be able to answer three main questions that I think will be of great importance to anybody who comes into first contact with the concept of biomass gasification. Firstly, I would like to tackle the issue of what is biomass gasification. Now, this will be followed by attempting to explain the promise that biomass gasification holds before proceeding to give a short introduction of how biomass gasification works. So what is biomass gasification? In the hierarchy of biomass gas conversion processes, there exist two main conversion pathways: bioconversion as well as thermal conversion. The bioconversion, or wet process, is witnessed in natural phenomena such as digestion to produce methane, fermentation and distillation to produce ethanol, as well as extraction processes to produce rubbers, chemicals such as rubber resins. On the other hand, thermal conversions, also known as the dry conversion process, involves four main types: liquefaction, combustion, pyrolysis, and finally gasification. Therefore, specifically, gasification is a process that converts organic or fossil-based carbonaceous materials into carbon monoxide, hydrogen, carbon dioxide, and etc. Now, this is achieved by reacting the materials at high temperatures, often above 700 degrees Celsius, without combustion, with a controlled amount of oxygen and steam. Gasification has become increasingly important due to its many advantages. Firstly, much of the world has started to grow on this process that has been around for more than 1,000 years. Currently, world reliance on biomass energy has increased to 14% of total energy consumption. Secondly, many industrialized countries are reconsidering the involvement of biomass in their energy systems due to mainly its carbon dioxide neutrality and renewable nature. Now, biomass energy is derived from plant sources such as wood from natural forests, waste from agriculture and forestry processes, and etc. So therefore, it's a natural process that all biomass ultimately decomposes to its molecules with the release of heat. And the combustion of biomass imitates this natural process, so the energy obtained from biomass is a form of renewable energy, and it does not add carbon dioxide to the environment, in contrast to fossil fuels. Lastly, it competes well with fossil fuels because it is renewable and with soft energies like solar and wind on account of its energy storage capabilities. So moving forward, the concept of what gasification really entails should be touched upon. Now, gasification is a process of conversion of solid carbonaceous fuels, like I said earlier, into combustible gas by partial combustion. Now, the resulting gas, known as producer gases, is a mixture of carbon monoxide, hydrogen, methane, carbon dioxide, and nitrogen. Now, the producer gas is more versatile in its use than the original solid biomass. It is burnt to produce heat and steam to be used in gas turbines to produce electricity. In short, this process takes in unusable or low-value wastes to produce a high calorific value gas. Now, in the course of this introduction, I raised it up at the start that we would like to answer the three questions of what, why, and how. So to recap, biomass gasification is a thermal conversion process, a dry process that converts solid waste fuel into high calorific producer gases. Now, it is precisely useful because of its carbon neutrality owing to its close imitation of natural bioconversion processes. Lastly, we burn these producer gases to produce heat and steam, producing electricity through the running of gas turbines. So moving forward, I've also conducted a literature review on the topic to let us gain some further insights into the topic and glean off what other respective scholars around the world have published. So to kick things off, we start with looking at the different types of gasifiers available on the market. There basically exist three types of gasifiers, namely fixed bed, fluidized bed, and entrained flow gasifier. In this particular study, we'll be focusing on the fluidized bed gasifier, one which has high reaction rates and effective mixing inside, so it is widely used in medium and large scale biomass gasification. Now, gasifiers have four distinct reaction zones: the drying zone, the pyrolysis zone, the combustion zone, as well as the reduction zone. Now in gasifiers, pyrolyzed gases and moisture generated in the pyrolysis and drying zone respectively flow downwards. Now the pyrolysis gases pass through the combustion zone, followed by a hot bed of char which is supported by a grate. Now biomass is fed to the gasifier and oxidized in this zone where continuous air is supplied from two air nozzles. Now the heat generated in this combustion zone is transferred to the pyrolysis and drying zone. Released heat from the biomass combustion processes raise the temperature of the biomass particles resting above the combustion zone and thus get pyrolyzed. Now the reduction zone signifies the location of the bulk of gasification reactions, including char reduction reactions and tar cracking. Hence it controls to a great extent the yield of the syngases or producer gases, which in turn define the gasification efficiency. So a look at scholarly work around the world has yielded some interesting findings. Firstly, Sheng in 1989 introduced the properties of biomass gasifiers and the gasifying reaction processes. Now, various fuels usually considered unusable or low-value waste, such as sawdust, wood chips, corn cobs, nutshells, rice husks, etc., were used in the biomass gasifier to produce a high calorific value gas. Now, Mascio et al. In 1994 studied the influence of the operating conditions of gasification of biomass at a pilot plant scale. Now, this was quickly followed by Jorapur and Rabneshi in 1995, who developed a gasifier running on chopped sugarcane leaves. Now, in 2002, Zinal performed experimental studies on the downdraft gasification of using wood chips and charcoal in order to assess the potential of the sawdust as a biomass material. Wander et al. In his study used a fixed bed, downdraft, stratified and open top gasifier to see whether the potential of sawdust as a biomass material was feasible. Now in more recent and similar experiments, Jana Ray conducted an experimental investigation of the temperature field inside the gasifier, followed by a high-fidelity numerical simulation using computational fluid dynamics to model the Lagrangian particle-coupled evolution. Now, the temperature distribution and the evolution of species are computed and compared with experimental results and with the ideal equilibrium zero-dimensional case. Now, at present, our study focuses on a Eulerian method to study the carbon dioxide gasification of biomass in a fluidized bed gasifier. So with respect to the study of the degradation of biomass via heterogeneous reactions, we will utilize the four heterogeneous reaction equations of char, together with the rate equations and kinetic parameters as a starting point. Now, having reviewed what exists in literature, a tentative plan has been scheduled in order to allow everyone to understand what I see going forward for the semester to come. Now, with my understanding of things, Dr. Chung has been heavily engaged in an ongoing experiment using All Power Labs biomass gasifiers. This translates into myself having to prepare for exposure to working on real-life laboratory environment in order to procure and analyze experimental data. Dr. Chung has also informed me of my task of developing a program for mathematical simulation. This means getting myself familiarized with the necessary programming languages required to engage in existing Eulerian methods to study the carbon dioxide gasification of biomass in a fluidized bed gasifier, as well as more detailed models such as the Euler-Euler and Euler-Lagrange models for more fundamental investigations of the fully coupled chemical and fluid mechanical aspects of the fluidized beds. Now lastly, a schedule is presented in order to put onto paper the proposed final year project plan for the upcoming few months. Now I've divided this into three aspects: preparation, knowledge, and execution. Now, in the preparation phase, familiarizing myself with MATLAB, Fluent, as well as other programming languages would be required throughout the course of the final year project. At the same time, knowledge gathering through literature reviews on the relevant theory, followed by further reviews on numerical simulation procedures for biomass gasifications once semester starts, is imperative to a successful project. Lastly, in the execution phase, the examination of existing experimental data and the actual carrying out of the project should be full steam ahead from the get-go once semester commences. Now, all this will be complemented by bi-monthly meetings with the professor. Now, thank you very much for your attention. It has been a pleasure presenting on my proposed plan for this final year project. Now, I look forward to a fruitful semester ahead. Thank you very much.